Okay, moving on to section 5. In section 5, we're going to learn a few different theorems about roots of polynomial equations. Now remember, roots, that's another way of saying our x-intercepts, or finding our zeros, or finding the solutions to an equation. In theory, if you wanted to, you could guess and check and see if you luck out, see if you can find one of the solutions if you're given an equation. If you're given an equation and you're finding the roots, you could say, okay, let's try plugging in 2 and see if that's a solution. Plug it in for x, see if your y value equals 0. If so, you lucked out. If not, you could keep trying. But there's an infinite number of possibilities, and maybe none of them would even work. Maybe your equation just has imaginary solutions. We don't necessarily know. Something called the rational root theorem narrows down our possibilities. So that instead of having an infinite number of possibilities that we would have to guess and check, we have a specific number. This rational root theorem makes solving certain polynomial equations really, really easy, especially the ones that before maybe we weren't able to solve algebraically. This rational root theorem makes it so we can. Okay, here's what it says. For a polynomial function, p of x equals a sub n x to the n power plus a sub n x to the n minus 1 plus our next power, and it keeps going until we have a sub 1x plus a sub 0 with integer coefficients And before I keep going, let's kind of talk about what this means again. A sub n would be whatever our first coefficient is, our leading coefficient. Whatever our coefficient times x to whatever our highest power is. And my next term is a sub n minus 1. My next coefficient, x to the next highest power. And it keeps going until we have a coefficient times x and just a constant term. Integer coefficients, remember what an integer is? We have to have a whole number. It could be positive, it could be negative, it could be 0. Here's what our rational root theorem says. Any rational roots must be in the form p divided by q. Where p is a factor of a sub 0 and q is a factor of a sub n. Now I know this is a lot, it seems pretty technical, there's a lot of variables here and not a whole lot of context, so bear with me for a second as we go through an example. This will kind of make a little bit more sense. But in normal person terms, here's what this means. Rational root is, remember, a number that can be written as a fraction. So if we have any x-intercepts that can be written as a fraction, they're in this form, p divided by q. P is any of our numbers that multiply to a sub 0, any numbers that multiply to our constant term, and q is any number that multiplies to our leading coefficient. Going through an example is hopefully going to make this make a lot more sense. So let's dive in with example 1 here. In example 1, we are trying to find the rational roots of our equation 2x to the third minus x squared plus 2x plus 5 equals 0. When you're using the rational root theorem, we need to find what p could be and what q could be. What are our options for our numerator? And what are our options for the denominator? Now our numerator again, p, that has to be a factor of a sub 0. So in this case, what numbers multiply to 5? You're probably thinking, okay, 1 and 5. 1 times 5 equals 5, but we also could do -1 and -5. So I'm going to do this instead of just listing 1, 5, -1, -5, plus or minus for each. And then for our denominator, q, that has to be a factor of our leading coefficient. In this case, what numbers multiply to 2? Could be 1, could be 2, but it could also be -1 and -2. So these are all of our combinations of numerators and denominators. Or this gives us all of our possibilities, I guess, for numerators and denominators. We have to figure out all the possible combinations. So I could have +1 over +1, or I could have +1 over -1. Or I could have -1 over -1, or -1 over +1. But either way, that gives me these two options. 1 over 2, or -1/2. And then 5 over 1, or -5. And finally, 5/2, -5/2. So to get these, I'm taking each possibility with the numerator, pairing it with each possibility for the denominator. Nice thing about the rational root theorem, instead of having an infinite number of rational roots, these are our only possibilities. Let's check them. So I'm going to take each of these values and plug it in for x in my equation. If I ever get a y value of 0, that tells me it's one of our rational roots. Now we have a couple different ways we could do this. The easiest way I like to do this is to go in my calculator, go to y equals, and type in that equation. Then go to your table. We can scroll through here and that would tell us our whole number possibilities, but an even easier way that will help us get some of our fractions in there is to go to table set. So I hit second, table set up here, and change the independent variable, which is x, to ask. I want it to say ask instead of auto. Now when I go back to table, I can enter a value for x. So if I wanted to check here, I can enter 1 for x, 1 enter, and it tells me what my y value is. And then I can keep going. -1 is 0. Since I get 0 as my y value, that tells us that's one of our rational roots. But let's keep going. Since our degree is 3, we could in theory have 3 different rational roots. So let's check, see if we have any more. 1/2, -1/2, and I'm going to keep entering a couple more before I write these down. 5, -5, And then my last root that we have to check, 5 halves and negative 5 halves. So this tells us that our only rational root for our equation here is at x equals -1.